All right. So, like I said, I'm going to start off with a little kind of example, just to give you a feel for what we're attempting to do. And then when we get into the actual problems, that's where it starts to get tricky. But if you understand the concept, then you're going to be in a much better place to be able to do some of these problems. There's two kinds of situations that we're talking about today. But first I'm going to start off with something that is kind of unrelated. Okay, and I taught this yesterday. But think about an infinite series. Okay, you add up the terms forever and ever and ever. If you add up a certain number of those terms, that's called a partial sum. We've talked about that before. You're only adding a portion of all of the terms in the series together. That's what a partial sum is. Okay. And obviously, we can't add up an infinite number of terms. It's impossible to do. There will be more terms after we die. So you can't do that. So it's not feasible, but it's also not necessary. Okay. The remaining terms, this is where we get conceptual. Okay. So we add up the number of terms we've decided to add up. All the other terms that go on forever that we have not included in our sum are called the remainder, sometimes called the error. And the reason that it's called the error, because obviously it's called the remainder for obvious reasons. It's the remaining terms. It's what's left over. The error is we're going to take a partial sum and probably use that to approximate the infinite series. And so it's going to be off, right? Because there's all these other terms that we never added in. So what we're going to be saying is we have this partial sum. We're going to be okay if we leave off, the rest of the terms, but we have to acknowledge that our partial sum and the actual sum of the series are going to be off. And how much it's off is the remainder or the error. Okay, that's the concept today. And we have two different scenarios that we're looking at. So if you can kind of get your head around that, then this shouldn't be so, okay? Generally speaking, the more terms you add, the smaller the remainder. Okay, which means the size of the error shrinks. The more terms you add, the smaller the error is. The more terms you add, the closer you get to the actual sum. And therefore, the error goes down. A lot of concept here. Here's a visual. Okay.
Is that like S integral or S?
No, this is the sum. The infinite sum equals the finite sum, which is the partial sum, plus the remainder, right? So I'm going to take a partial sum, which is a finite sum. I can add them up. And I'm going to add to it all the rest of the terms, and that represents the remainder. Okay? And so together, these two things do equal the infinite sum. Now, this is not an official mathematical notation. This is Mr. Zukin made up a notation, and is just kind of giving you, again, reinforcing the concept in sort of a mathematical way. Yes. The remainder goes on infinitely, but it's still going, it's going to have all of the rest of the terms in. Okay? And there are infinitely many terms, but it will have all of the rest of the terms in it. Okay? So yes, these two, I have a finite. This does go on and on forever. But again, as we've talked about with series and divergence and convergence, like a lot of the times our series will converge, even though we can add an infinite number of numbers on. So here's an example. Now this is not an example of a type of problem you're going to do. It's going to, again, I want it to kind of reinforce the concept. Okay? So here is a series. It is an alternating series. We can tell by that -1 to the n over n squared. And I wrote the first bunch of terms out. Okay? And I'm gonna choose to find the fourth partial sum. okay, meaning the first four terms. Okay? And this example is going to be sort of the basis for how we can figure out sort of what the error will be, or what the remainder will be. So here's what I'm going to do with these terms. Okay, we're gonna take the first four terms, the fourth partial sum, and I'm just going to call this R4 because it's the remainder after the fourth partial sum. You can name it whatever you want it. I'm just putting a little 4 there to indicate this is the remainder based on the idea of the fourth partial sum, or the partial sum of the first four terms, however you want to do it. Okay? Now, the other thing we do know, what do we know about this series? If I didn't have any of this, what do we know about it from the tests that we've already learned? Right, the limit of 1 over n squared approaches 0, right? This is convergent by the alternating series test, okay? Which means there's a sum for this, even though there's an infinite number of terms, okay? Now, I went ahead and did the calculations, and then I'm going to play with some algebra just to prove a point here, okay? So what's in green here is 115 over 144. You can just believe me. Now, I did something here with these remaining terms, and after you write it down, I'll kind of explain why I did what I did. So what I did, the manipulation that I did, is I factored out a -1, and then I grouped two terms together. Okay, so I factored out a -1, that changed that to minus, factored out a -1. Okay, now here's the reason why I did that. Can we agree that 1 over 36 is less than 1 over 25? Okay. As the denominator gets bigger, the fraction's value gets smaller. Can we also agree that 1 over 49 is less than 1 over 36? So what is this type? What kind of number is this? Small, and what? It is positive, right? If I take something smaller away from something bigger, I get something positive. We already agreed that 1 over 25 is bigger than this, but if I took this away from it, I would still get a value here that is less than 1 over 25. Agree or no? Okay, so I'm going to take something smaller away from this. And then if we keep moving with that idea, this is smaller than this, so I'm taking something even smaller away now. So I'm reducing the value of 1 over 25 by a little bit every time. I'm taking a little bit off, a little bit off, a little bit off, a little bit off. Okay. This all is the error, the remainder. Okay. So the highest value, what is the absolute highest value that the remainder could be for this example? Yep, the highest possible value that I could have is right here. And it just gets lower, right? As I start subtracting things from it, that number gets smaller. Now, if these numbers, these differences are infinitesimally small, then it's like I'm not subtracting anything from it. Okay? Now, here's the thing. What we can gain, and this is true for alternating series, okay? What we know is that that remainder is less than or equal to 1 over 25. It could be equal if those subtractions are 0. But generally speaking, they're going to be smaller than 1 over 25. Okay? So here's the thing. Here's the takeaway. Okay? And this example is just one example of that, and I'm leading toward the general idea. The remainder for an alternating series, okay, is always going to be, at most, the next term beyond the partial sum. Okay, so if I took the partial sum of 5 terms, then the biggest the remainder could be is the 6th term. If I added up the first 10 terms, the biggest the remainder could be is the 11th term. It's always going to be the next term. And this is just kind of an illustration of that. Okay. So let's get into that concept even more now. All right. It's got to be a converging alternating series. Okay. This is on page 211. For a convergent alternating series, when you're going to approximate the sum using only the first n terms, the error is the nth plus 1 term. He wrote it as n plus first term. I can't decide which it should be. I want to say it's the nth plus 1 term, but it doesn't matter. It's the next term. It's going to be less than or equal to that. Okay. And in that example, we kind of illustrated that. The error can be as big as the next term, but it's probably going to be smaller than that because we're going to chip away at it and reduce it by subtracting. Okay? So here's what that looks like in Mr. Zukin speak. Okay? And then I'm going to hit you with the actual formula that he uses in the book. So my infinite sum equals the partial sum plus the remainder. This remainder will be the next term. Okay, so if I add up the first n terms, the n plus 1 term is where I find the biggest possible value for my remainder. And here's why we look for this. Okay, as I mentioned at the beginning, if I'm going to use a partial sum to approximate the actual infinite sum, the infinite series, we have to be able to decide how far off we are from the actual series, from the actual sum. And what we're going to be able to do is create an interval under which my sum probably actually is. Okay, so we're going to find this partial sum. We're going to say, okay, there's an upper bound for this sum. There's a lower bound for this sum based on whatever my error is, or whatever my remainder is. And then we can say, okay, we can safely say the sum of this series is in between here and here. And again, the more terms we take, the smaller our error. And so we can zero in even closer and closer and closer to what that range of values should be for the series. Now here's how he describes it in the book. And he even acknowledges, he's like, this expression looks far more complicated than it really is. Okay, well, here, I made it simpler for you. The first unused term. Now, he writes it in terms of Taylor polynomial. Okay. So the next derivative of the wherever we're centered, okay, times x minus wherever we're centered to the n plus 1, all over n plus 1 factorial. The long story short is it's just the next term. Whatever that next unused term is, if I took a 6 partial sum, then it's the 7th term. That's the key. That's your takeaway here. It's just the next term for your remainders. And that's why I went through that example at first, because that example, I think, seems pretty clear, right? I mean, it's not easy, don't get me wrong. But you can see it. And that's what I was trying to illustrate. So in some of these examples, I'm going to illustrate a couple different things because you have to know what they're asking. You have to know what you're trying to find. And the way that questions are worded, you just have to be careful. And this kind of stuff is going to show up on the exam for sure. All right. Here we go again. Waiting. There. All right, example 1. So this one just says, approximate the sum of the first 6 terms. Approximate the sum of the series by using the first 6 terms. So what we're finding here, what you're finding here, is this. That's all. 6 partial sum. So go ahead and do that. So here are the first 6 terms. Hopefully that's what you got. And it alternates from, positive to negative. And maybe you're getting your factorials down. Maybe you got it to 5. 6 is 720, but I don't know if you got those down yet. So this is approximately equal to 0.63194 repeating. Okay? Hopefully that's what you got. Now, the next question that kind of follows after this is trying to figure out how far away this is from the actual sum. Because this is just the sum of the first 6 terms. We need to know what the sum is of this entire series. Now, I can tell you that this series does converge. It does have a sum. We haven't learned the rule yet as to why that is true. But we will. So just trust me on that one, okay?
Today?
Not today, no. Yeah, not today. That's coming, okay? Now, what it's saying here is find the upper bound for the remainder for the approximation, for example. Let me translate what that means, okay? Our remainder starts at a highest value and it just starts going down. So the upper bound, what it's saying is what is the maximum possible value for the remainder? That's all it's asking. It seems like maybe a strange wording, but that's what it's saying. What is the biggest possible value for the remainder? What is the biggest possible value for the error? Well, we should know how to find that now. What is it? Where would I go? What would I look for? The 7th term. The 7th term, okay? The 7th term is going to be where remainder is. The remainder is less than or equal to the 7th term. So that means the biggest possible value the remainder can be is the 7th term. Now, it's in absolute value. Okay, notice that. So especially with the alternating series, there's sometimes it's negative, sometimes it's positive. But for the remainder, it doesn't matter. It's just the absolute value of that. Okay, so the 7th term is 1 over 7 factorial. This is approximately 0.000198 Now, maybe you can see why I didn't go to three digits, right? I go to 3 digits, I have nothing. 0.000 is nothing. And this number is really small. You can, yeah. I will tell you maybe why you don't want to here in a minute. Yeah.
Can you write it in scientific notation?
Yeah, that's fine. You can do that. If you're clear, if you're comfortable with what scientific notation is, because sometimes I have kids that stare at the screen and don't know what that means. If you're clear about that, that's fine. But I like to write it out in decimals because, let's face it, this number is pretty small, right? It's less than 1 over 1,000. Small. Which means, just again, concept. If I find the first 6 terms of this particular series, I'm pretty close to where the actual sum is. Because I'm only off by that much, at most. And I'm probably off by less than that. So that's a pretty decent approximation. Now, let's keep moving through the examples. Okay? So the next example says, find the lower and upper bounds for the actual sum. So now we're going to take that remainder and we're going to use it to figure out what's the possible upper bound for the sum and what's the possible lower bound of the sum. Let's create the interval for where the sum actually probably lies. Okay? And this is as simple as taking our 6 partial sum, add the remainder to it. Okay, take our 6 partial sum and subtract the remainder from it. And that's where my bounds come from. Okay? Intuitively, that shouldn't be that challenging. Okay, so my remainder lies here, right? At the upper end, it's 0.001984. The lower end, it's negative. So I'm just going to add those two things. to my partial sum, and that will give me my upper and lower bound. It will give me my interval for where the sum actually lies. Okay, and that's what this is. Okay, we found out that it was 0.63194 repeating, and so now I can create an interval for where my sum is. And of course, if I took the 7th or 8th or 9th partial sum and used the 10th term as my error, that error would go down and I would get closer and closer and closer to it. So if we use the idea here, so here's where the interval of my sum, the actual infinite series lies in between 0.6319445 and 0.6321429. If I use the 3 decimal place rule, we have it. Because that's 0.632 and that's 0.632. So in this case, finding the 6th partial sum is a really good approximation. I mean, and even if you look at the 6th partial sum, if I rounded this, it's 0.632, 0.632, 0.632. We're right in there. Now, obviously, it's off a little bit, right? And that's why I went so many other decimal places, because I want you to see that. Now, the problem is going to ask you how accurate you should be and how big of an error you're allowed to have. Okay, and that's one of the big challenges in this section with alternating series remainder, okay, is figuring out how far do you need to go with your sum. Okay? Questions? Let's do another one. Example 4. So here's what I'm talking about. It's saying approximate the series with an error of less than 0.001. Okay, so you have to figure out how many terms you have to add until your error gets less than that. Now, one of the things that's really important with these problems, because there's going to be a lot of fractions, this is 1 over 1,000. Okay? And the reason I put that up there is because, as we talked about earlier, as the number on the bottom gets bigger, when the numerator is 1, the fraction is getting smaller. So what this question is really asking is, what term is smaller than that? Because that's the next term. And then I just have to add up all the ones before that. So if you can figure out which term is less than 1 over 1,000, then you've found where the error is less than 0.001. And then you can take the partial sum. So this is the challenge for this problem. How many terms do you have to add up until you find a term that is less than that? And so here's kind of the way you do it. Okay? This is kind of what I've just been talking about. Find the first term whose absolute value is less than 0.001. And then add up all the terms in front of them. Let me just kind of model how I would do this problem. Right? Obviously, you need to start finding some terms, right? Because in the end, when you find that the first time the number is less than 1 over 100, then you can stop. But even then, you still have to have all the other terms before it. So I would just start going, okay, what's the first term? So we're going from 0 here. So what's the first term? 1. That's not less than 0.001. So I got to find a second term. All right, the second term is when n equals 1. So that means this is negative. This is 2 times 1. What is 2 factorial? 2. So it's minus a half. Still not less than 0.001. Okay. Now I got to find the third term. So now I'm going to plug in n for 2. Makes it positive. That makes this a 4. What's 4 factorial? And if you want to see the decimal, there it is. Still not less than 0.001. Okay? Fourth term, that means n equals 3. Got a negative. 6 factorial. 720. Okay, and so on. You get the idea. Now, 1 over 8 so 1 over 720 is not less. 1 over 8 factorial, the next term, is. Right? What is 8 factorial? So, tell me.
1 over 40,000.
320?
Yeah.
Okay. So in terms of fractions again. 1,000. There we go. Like, whoa, that didn't work. 720 is less than 1,000, but then I finally get a number that is greater than 1,000, which means the fraction is smaller than this. Okay. So this is the place where I know I can stop. Whether you think about it in terms of fractions or decimals, I don't care. That's up to you. All right, so what does this tell me? What does this represent? The max remainder, right? And then I'm going to have to add up all these. So there's my remainder. And then I actually have to find the sum of those. So whether you do it with fractions or decimals, probably fractions is going to be more accurate. And on your calculator, you have all of that in there. And so instead of approximating, you can actually go up and highlight the one and hit enter, highlight the one and hit enter, and it'll give you a pretty accurate sum. All right? And the sum is 0.54028. Okay. We already have our remainder.
No one ever taught me that. You need to copy and paste.
Yes, you can copy and paste in your calculator. You know that?
No.
Oh. Well,
It doesn't come that well. I mean, it does, but I'm
learn something new every day. If you want to. All right. So, the answer to the question. We're approximating this. Here's our approximation with such a small error. Think about that. This is, the first time I have a decimal that's not 0 is the 5th place. Well, I have 5 places here. So my sum could be 0.54030. That's pretty good. That's pretty accurate, right? That dials us in pretty close. So that's the first example for that. I think I'm gonna write this. Let's do another one. Now it's saying use an elementary series for that last problem to find the value of the series. In example 4. Down over here. Now, just as a refresh. There we go. Okay. Here are our elementary series. Okay. Which one of these looks like example 4? The cosine, right? The denominator is 2 factorial, 4 factorial, 6 factorial, 8 factorial. All right, we have our negative 1 to the n. The part that's missing from this is what? The x term. There is no x term in example 4. Okay, so in terms of cosine, what does this equal? X to the 2n, what does it equal? Say it. 1. It equals 1. So from there, it's just a matter of figuring out what we're actually talking about. So for example 4, if I'm going to figure out what it is, if x to the 2n equals 1, we are taking the cosine of 1. Okay. So, plug it in. What's the cosine of 1? So if you think about that, I even mentioned that number, right? Because our sum was 0.54028. Well, the error was 0.00002. Pretty accurate, okay? All right, that is alternating series remainder. That's the easy one. Here's the harder one, okay? Now, if the series is not alternating, okay, finding the error is more complicated. Because let's think about what's happening in an alternating series, right? You add a little bit, then you subtract a little bit. You add a little bit, then you subtract a little bit. But as you're adding a little bit and subtracting a little bit, those numbers are getting smaller and smaller and smaller and smaller. Okay, because it's a convergent series. So it's starting to zero in on where it's going. Okay, when it's not alternating, think about it. If I have a series and I keep adding a positive number to it every time, it could theoretically grow and be divergent. Or same thing if I'm subtracting. Okay? So I'm just going to get into more of the formula. Again, I'm going to simplify this. This is called the Lagrange remainder or Lagrange error bound. They use those phrases simultaneously. They replace them with each other. They mean the same thing. Why can't I come up with the word that I'm trying to come up with? They all mean the same thing. Interchangeably. Thank you. You aren't just great math students. Thanks for your help. Okay. Interchangeably. Lagrange error and Lagrange error bound. I'm used to seeing it called the Lagrange error bound. Yes, Lagrange, ZZ top. Okay. Now, here's the thing that's different about this from the alternating. One of the things that's different. Now, there's some value in between our interval from X to C, wherever we're centered, where a maximum value occurs. And that is what this really is. It makes this derivative a maximum. Okay, so there's some value Z that's in between X and wherever we're centered where the derivative is maximized. Now, we can, and a lot of times like this, we can write it like this. We can just replace that derivative, the next derivative, because, right, it's still the n plus 1. The next derivative, we can replace the next derivative with an m and think about it that way. It's just the maximum. Okay? And so the maximum value of the n plus 1th derivative, the nth plus 1 derivative, or the n plus first derivative, I don't know. The next derivative is there's going to be a maximum value on that interval from C to X or from X to C, depending on which one's bigger. So most of the time, what these problems boil down to is finding that maximum of the next term. Okay. Here's a hint. It doesn't always happen, but it happens a lot of times. It usually occurs at the endpoints. Not always, but you're going to check the endpoints of that interval and see, hey, what's my derivative here? Is it as big as it can be? Most of the time, that's what's going to happen. So let's go through some examples. So this is where it all connects to our Taylors and Maclaurens, okay? So we're going to estimate e to the second. And I understand we could just go e and then you press the calculator and you get I get it, right? Of course, we're going to use examples that are accessible to us first to get good practice at doing things. All right, now it says estimate e squared using a Maclaurin polynomial of degree 10. Of degree 10. I know, you're thinking, I'm going to have to come up with... No, you're not. Relax. You're not going to have to come up with the first 10 terms. Okay? For e to the x. Now, I'm going to write some of them out. Just to kind of give you a feel for it, right? So e to the x we know is 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial, right? Hopefully you remember that. And so I'm going to write the first few out and then put my 3 dots and then we'll go to the end. X to the 10th over 10 factorial. This is where making sure you know your elementary series are important, okay? Because being able to use that and produce it quickly is going to save you time. Now, what we're going to do, since it's a Maclaurin, it's centered at what? 0. Okay, so I don't have to worry about x minus anything. But what is x actually going to equal in this problem? 2. Okay, so I'm going to replace all the x's with 2's. Now, I am confident, first off, you all know where the factorial button is in your calculator? Yes? Okay. I haven't figured out a way to make it a shortcut or anything like that, so if you figure that out, let me know. But in the interest of time, I believe you could type this in your calculator just fine, but I'm not going to. I went ahead and found it for you. Okay. It's a 7.388994709. Okay. Remember that E is 2 point something. I forget, 2.3 something. 2.7. I don't know. 2.71. 2.71. Okay. It's Pi Day. We should just know the pi numbers. It's fine. All right. Anyway, so there's my estimate of e to the second using a 10th degree Maclaurin. Okay. Of course, we need to figure out how close this is to the actual thing. But this is not an alternating series. I can't use the alternating series remainder. I have to use Lagrange. Okay. So we're going to use the Lagrange form of the error, Lagrange error bound, to estimate the accuracy of this. So we're going to find that remainder. Now, what's important here is we have to understand what our interval is. Bless you. Okay. So what is our interval here? What interval of values are we working with? Well, what are we centered at? What is x in this problem? 2. Okay. So the interval that we're curious about is when x equals 2 and c equals 0. And so what I have to be able to do is figure out the maximum value of the derivative of which derivative? Is it the 10th derivative?
No.
It's the next one. So I need to know what the maximum value of the 11th derivative is on the interval from 0 to 2 of e to the x. Well, fortunately for us, the derivative of e to the x is always e to the x. So the question is, what value of e to the something between 0 and 2 inclusive is going to give me the highest value? 2. Yeah. 2 is going to give me the highest possible derivative there. Because obviously e to the 0 is 1, e to the 2 is 7 point something. Okay, so the highest possible value is going to occur at 2. Now, in this case, our maximum value is e squared because it occurs at 2. The maximum value of the 11th derivative over the interval is e squared. So in our formula, where I had that crazy looking derivative thing, it's just e squared. Okay? No relationship to Einstein's theory of relativity. Okay, so here's where my Lagrange error bound is, and he will use LR, Lagrange remainder. It is less than or equal to absolute value of e squared. That's the maximum. I could have, extended it and went like this over the whole thing. That would have been fine. Whatever. times 2 to the 11th, because again, it's the next term, over 11 factorial. Everything is always the next term when it comes to remainder and error bound. I don't know if I figured out what that was. Estimate actually the partial sum. Yeah, I did. Okay. So I created an interval of the remainder. So the error is in between 0.00379 and negative 0.00379. That's how far off we could be from the actual e squared. And I'm guessing, even if you typed e squared into your calculator, you wouldn't, well, I don't know. How many digits do you get? Type e squared in your calculator. How many digits do you get? Do you get beyond the 9? One more digit? Yeah.
Yeah, 9 after this.
So,
Well, I was counting the one before the decimal.
that's fine. 3, 8, 9, 0. Okay. So we're off a little bit on the calculator, right? As we should be. And it happens right in around here, where all of a sudden it's off a little bit. Well, if I added these terms here with these 9s, those are going to push some of these numbers up with our error. Okay. All right. Hopefully that makes sense. Now, are there questions before we move on to a different type of problem? Yes. All right. Example. If the fifth derivative equals 700 sine x and x equals 0.7, and if x equals 0.7 is in the convergence interval for the power series centered at x equals 0, find an upper limit for the error when the fourth degree Taylor polynomial is used to find f of 0.7, right? There's just a lot there. But fortunately, they give us the fifth derivative because they're talking about a fourth degree Taylor. They give us the fifth derivative, the next derivative, which is going to allow us to find the maximum, right? Because in order to do this, we need to find the maximum, and I need to have the fifth term. And we can do that using our Taylor polynomial. So they tell us what x is. They tell us what c is. Okay. X is 0.7. C, they tell us we're centered at 0. So the interval that we're looking at, bless you, is from 0 to 0.7. The question is, where does the maximum of this derivative occur? Now, and it has to be in between these two numbers, right? We know that the maximum value for sine is what? 1. Where does it occur the first time? Pi over 2. What is pi over 2 as a decimal? Like 1.57, something like that. Okay, so we're not going to ever hit the absolute maximum on this interval. Between 0 and 0.7, we're not going to get to 1. Right? The sine of 0 we know is what? 0. So that's going to be as small as it can be. Now, as the angle is moving up to approach 1.57, right, is the sine of 0.7 going to be bigger or smaller than the sine of 0? It'll be bigger. Are the values in between 0.7 and 0, are the sine of those values going to be bigger or smaller than the sine of 0.7? Smaller. So where is the maximum going to occur? 0.7. Okay. That's the key here. The max of the derivative occurs at 0.7. And like I said, a lot of the times, it's going to be one of those endpoints. So what I would do is test the endpoints. And this is one of those ones where you can play with your calculator a little bit. Maybe you don't believe it. And you go, all right, sine 0.5. See what it is. Sine 0.6, sine 0.7. You can do that in 2 seconds. Go, okay, I'm convinced it's 0.7. You don't have to find all the values. I mean, for that matter, you could put sine of x into your calculator in the y equals screen, make a table that goes by 0.1s, and go over to it real quick. All right, anyway. It occurs at 0.7, but what is the fifth derivative at 0.7? Because that's what we really need to figure out. What is the fifth derivative at 0.7? What do I do? How do I find it? Yeah, just plug it in. 700 sine 0.7. What is it? I stopped at 3. Okay, so the maximum value of the fifth derivative that occurs at 0.7 is 450.952. So I got a big chunk of my formula now. Again, I know my x, I know my c. It's the fifth term we're talking about here. So this is what the Lagrange error bound is going to look like. Okay, the maximum value, the x minus c, raise it to the fifth power because we're talking about the fifth term, which means it has to be over 5 factorial. Now, it says find the upper limit of the error. So that means all I have to do, since this is as big as it could ever be, is figure out what that is. I figure out what that is and I'm done. So I will do that for you. Save us a little time. 0.631596. That feels like a significant error based on what we've been doing before. But we don't really know anything about the function we're looking at, the series we're looking at. We have no idea. They've given us no information other than do the calculation. Here, practice working the error. Okay? So I don't know if that's a bad estimate or not. It might be a great estimate. All right, we have one more example to go through, and then we can have pi. Last one, example 9. Sixth derivative is a positive decreasing function. That's important. Find the error bound when a fifth degree Taylor polynomial centered at 4 is used to approximate f of 4.1. Assume the series converges 4, x equals 4.1. Okay, so when we're doing these things, right, we need lots of information. We need to know x, we need to know c, we need to find the maximum. We need to know which term we're talking about, and then we got to use the next term. Right, they give us information about a fifth degree Taylor. They give us the sixth derivative, which means for our Lagrange error bound, we're looking at the sixth term. The sixth term. Okay. Why don't you try this one? Try setting this one up and let's see how you do. So I've got my x, I've got my c. We don't have a function. Like in the last problem, we had a function at least to try to figure out what the maximum would be. But we don't have that here. Okay? Here's the key word in this problem. The key word in this problem is that it's a function that is, the derivative is positive and decreasing. Let's make sure we understand what that means. Okay? Decreasing, that means as x is increasing, the derivative is decreasing. Okay? So where is the highest possible value going to occur? All right, 4 is bigger than 4.1 because as we go from 4 to 4.1 to 4.2, the derivative is going down. That decreasing is the big key there. The maximum occurs at x equals 4 because 4 is bigger than 4.1. And that's where I'm testing my endpoints. All right, we're not going to be able to know what the maximum is here. We can't find it out. And that's probably what was hanging you up because we don't have a function to really work with. But I can set up the general idea of what the Lagrange error bound should be, the Lagrange remainder. Okay, I'm going to have my maximum value, whatever that is, at the fifth derivative. Or sixth derivative, excuse me. And so we need to be specific about the idea here that this is at x equals 4.
For X there.
I mean, I guess you could. Yeah, I guess we could do that. Yeah, let's do that. Let's just make that a 4. You're right. I like that better. Yeah, let's make that a 4. Okay. All right. And then we can't really get anywhere with that. We can simplify it down a little. That's really all we can do. Okay. So we can't actually find the error bound, but we can come up with an expression that represents it. Okay.